Hello everyone. Welcome to the last lecture of the series of data-driven model predictive control. In this lecture, we will be discussing some recent advances and applications of data-driven MPC. Here is the overview of this lecture. We will start with the recent approaches in data-driven MPC. Then we will briefly discuss on the applications of data-driven MPC, which is then followed by the references for this lecture series. One of the recent development in data-driven MPC is the reinforcement learning, which becomes a popular research area nowadays. Reinforcement learning or RL comes under machine learning, and it can be considered as a model-free optimal control approach. It computes the optimal control policy directly from data by using various learning algorithms, and it also adapts its policy based on the feedback obtained from the system's responses. Recently in the literature, a few approaches for transformer-based MPC is also proposed. It can be considered as a data-driven NMPC approach, which uses the transformer model. And the transformer is a recently developed deep learning model, which uses the attention mechanism for extracting dynamic relationships in the dataset. And in one of our recent approach, we proposed an extension of the state space neural network or SSNN, which is called SSNN with ordered variants or SSNNO. In this work, we use the idea of variance regularization to order the states in terms of its variance computed of the training data. And the regularization time is used for ordering the states in decreasing variance. One of the main motivation for this SSNNO is that in general in nonlinear system identification, the model order or the dimension of the state vector is unknown. All the available information consists of the input and output data. And identifying the number of state variables or the model order is a challenging task, which is commonly solved using trial and error methods. This motivates the idea of this SSNNO, in which we use this ordering idea for identifying the model order. In the next few slides, we will be briefly discussing this idea of SSNNO and also how it can be used for identifying the model order in state space models. In the SSNNO, the variance ordering is achieved by using a modified loss function as in equation 1, in which this first time is similar to the standard SSNN loss function, which is the output prediction error. This second time is our contribution, which is the state-based regularization term used for ordering the state variables. And this third term is the weight regularization term, which is commonly used in neural network models. Here, this capital XD is the predicted state sequence, similar to SSNN, and XD bar contains the mean predicted state vector as its elements. And this WX is chosen as a diagonal matrix, which contains this weighting matrix elements W1 till WL. This second term L2 can be expanded as in equation number 2, where we have weighted some of the state variances, where Vx1 is the variance of the first state variable and Vxl is the variance of the nth state variable. And by choosing these weights in an increasing order, we can result in a SSNN model in which the state variances are in decreasing order. Using this ordering, we can find the number of significant variables in the state vector, and we denote it by S. This can be computed by defining a threshold value delta, which can be chosen very small. And we can identify the number of state variables with the variance greater than delta. And using which we can partition the state vector into two parts, XA and XB, where XA contains the first S variables for which the variance is greater than delta, and XB contains the remaining L minus S number of variables for which the variance is nearly 0. Here we can see that the variance of this XB is nearly 0. Therefore, even if we replace XB with its mean value, the model prediction does not get affected. This idea is used in model order reduction in the proposed SSNNO, in which we replace XB with its mean vector XB bar and reabsorb this in the model as a bias term. Then in the model, we will be only having XA as the state vector, and this XA will be is of order S, and which is just sufficient to predict the output with reasonable accuracy. Theoretical guarantee for variance ordering and a numerical simulation is also given in the paper. Next, we move on to the applications of data-driven MPC. One of the major applications where data-driven MPC can be used is these process industries, in which a true model of the system is very difficult to obtain because of the large and interconnected nature of the process. Therefore, we can use data-driven modeling and data-driven MPC for controlling these processes. And another application is mechanical systems such as robots and aerospace systems. Currently, RL is commonly used for controlling robotic systems, and we can also use other D-MPC algorithms for similar applications. Another major area is network systems, which consist of complex interconnected systems such as power grid, cyber physical systems, etc., where obtaining a first principle model is difficult. And in general, data-driven MPC can be used for any application where a first principle model is difficult to obtain or not accurate. Next, we move on to the references for this lecture series. This lecture series is mainly based on my recent survey paper on data-driven MPC, for which the link is also given in the description. For more references on linear system identification and data-driven linear MPC, these references can be followed. And for data-driven nonlinear MPC and in general MPC, these references can be used. That leads us to the end of this lecture and also this lecture series. In case of any suggestions and for more details, feel free to contact me on this mail ID. And thank you all for watching.